In this video, we are going to look at classifying enzymes. And to start with, actually, let's look at just a little bit of terminology because you may have heard some of these terms. So assay, when we talk about that, we're talking about a test for protein activity. Enzymes are proteins, so we're going to use this term periodically. And we could be looking for many different types of activity. We could be looking for chemical change. That's mainly what we're going to be looking at right now. Okay, we could be looking at chemical binding, for example, binding oxygen to a carrier protein. We could be looking at chemical transport, so transporting a small molecule, looking for that protein activity. But right now we're really focusing on those chemical changes. And here would be an example. If we wanted to do an assay for the enzyme lactate dehydrogenase, okay, this one is based on the fact that one of the products, this NADH, absorbs in the UV range. And so we can monitor, based on that absorption, we can monitor the concentration of NADH and learn something about the amount of our product. Let's look at several things here. First of all, right here, notice we've written the name of the enzyme. So for enzyme-mediated reactions, we often write the name of the enzyme above the arrows. When you look right here, you can see that these arrows go in both directions. When that is the case, the enzyme can catalyze both the forward and the reverse reaction. Enzymes are typically named, okay, with the name of the substrate plus the chemical change that it's catalyzing. So if we look at lactate dehydrogenase, okay, we can assume that lactate right here is one of our substrates, right? And dehydrogenase. Now remember, this reaction can go in both directions, so we do see the chemical change going on here, and it can go in forward and reverse. Chemical change generally has one or two substrates, and sometimes that second substrate is called a co-substrate or a cofactor. Okay, so co-substrate, which would be the NAD plus here. This is a reaction where we are oxidizing lactate. Since that is the case, if it's being oxidized, right, so lose electrons oxidation, so it's losing electrons, something else has to be reduced, something else has to be gaining the electrons. And that's what our co-substrate is doing in this case. It's accepting the electrons. We see that as we go from here to our product, that this is reduced, okay, that the NAD plus was reduced to NADH. So that was our co-substrate. If we look at this reaction, actually we're going to look at a different reaction now. As an example. So this is a reaction catalyzed by carbonic, so we would write that over the arrows, anhydrase. Here's our carbonic acid on the right, which seems a little weird because we said we name it after the substrate, but notice that our arrows go in both directions. So this reaction can proceed in forward or reverse. So anhydrase, removing water. So since it can go in forward or reverse, it can facilitate the addition or the removal of water. This reaction and this enzyme are really important in biological systems. Okay, it catalyzes or facilitates carbon dioxide. So right here, being converted to carbonic acid. And then carbonic acid, being an acid, will donate a proton and it will continue on to form bicarbonate ion. And you might remember earlier we looked at that series of reactions that occurs in our bodies. The carbon dioxide going to carbonic acid to bicarbonate. the reaction is much, much faster. Okay, so enzymes can generally catalyze reactions, increase reaction rates by factors of something like 1,000,000 or more. In this reaction, we see when it's catalyzed about 10 to the 7th carbon dioxide reacting per second. If we look at what's happening over here, you can see that the carbonic anhydrase has these 3 histidine rings. These may not show up on the picture. You can see one there, and one there. Ones I just colored in there. So the histidine rings we can recognize in our picture. Okay. If we expand this, you can see right here we have the water molecule shown with those orange you see there. And if we look down here, we'll see a carbon dioxide coming into the active site. And the main thing I want to point out to you right here is this. This is a zinc ion. And when we look at that zinc ion, it is stabilized by those histidine residues and it's held in place. And then similarly, it holds that carbon dioxide and that water in appropriate locations so that they're in the right orientation to react. All right, so that was one thing I wanted to point out with that example. The other is these numbers. So we said, or I said, that enzymes are generally named by the name of the substrate plus the reaction it is facilitating, except for some older ones before they got organized, which have more random names. But we also have an enzyme classification system. So picture like the IUPAC for chemistry and things like that for enzymes. So we have this classification system. The first number, and we're going to look at these in a minute, is the general class. There's only 7 possibilities. The second number now is a little more specific, and it's going to give us some specific types of chemistry done by that enzyme in that class. We'll look at examples of that too. And then these last 2 numbers give us the specific form for the specific thing. So you might have carbonic anhydrase in one type of cell versus another, and it'll be a little different. Or maybe in one organism versus another, and it'll be a little bit different for those particular environments. All right, let's look at enzyme classification. I do not care if you know the numbers. So you don't need to know, for example, that EC1 means oxidoreductases, okay? I don't care about the numbers. But you should know the different classes and the types of reactions that they catalyze. So this top version facilitates redox reaction. When we look at transferases, it's what that sounds like, okay? They're going to transfer a group from one substrate to another. Hydrolases, it's talking about adding water, which generally causes a bond to break. Okay. Lyases, we're talking about breaking or making bonds. Isomerases, we're talking about essentially moving the order of attachment. So you could picture something like a chiral center, an optical isomer, where if we reversed a couple of those locations, now you have a different order of attachment. Ligases, we're generally going to have ATP hydrolyzed, okay, and it's going to release energy. And this last one's kind of interesting because it is actually not a chemical reaction here, but this catalyzes the movements of ions or molecules across membranes. So those are our main numbers. Those are the ones in this catalyze or indicated by this first number. Now this next one, you don't need to know these. This is just FYI. When you look at this, this is the type of thing we're talking about with that second number. Okay, if that second number, if we had a lyase and the second number was a 1, we'd be like, oh, that's breaking a carbon-carbon bond. If the second number was a 2, we'd know we were talking about a carbon-oxygen bond, and so on and so forth. Again, you don't need to know those, just as an example. Okay, so let's talk about chemical cofactors. So as we talk about cofactors, there are really two main pieces. You can have coenzymes, or you can have metal ions. So coenzymes are generally small organic molecules. And we can further break that down into two different categories, prosthetic groups or co-substrates. So we looked at an example of this a minute ago. NAD plus was an example. So you don't need to know that one in specific. Substrate. NAD plus was an example. Okay, but there's lots of other ones. This is an example, FAD, that we'll look at later. All right, so how are these different? The difference is that the prosthetic groups are bound to the enzyme. They stay there. They change during the process, maybe, but they stay in place. The co-substrate can enter and leave the active site. So these enzymes, some enzymes, need these coenzymes to be functional. And before, if we make the enzyme but the cofactor is not yet added, you'll see the term sometimes apoenzyme. Okay, so before cofactor is added, so it's not functional. We can look at some cofactors, so thiamine. When you start looking at these terms, it kind of starts sounding sometimes, if you really look at it, folate, like a multivitamin. You've got zinc, magnesium, and that's because as we talk about these cofactors, many of them are things that you need to consume in your diet, and then they get utilized in these enzyme systems. I left this in here just so we could go back and look at this again and say, remember, this was the cofactor now. The enzyme needs that in order to work. All right, let's practice. So we want to identify what class, this hexokinase, what class of enzyme this is. So pause and take a minute and look at it, see what you can come up with. So if I'm looking at this, I'm going to first say, hydrolase. I know that that is adding water to break a bond. That does not seem to be what I'm doing at all. I'm going to cross that one out. I know isomerase, dropping down to the bottom, I can cross that one out too. That's the rearrangement of the order of the atoms. That's not what we have. When I look at ligase versus lyase, so first of all, when we look at let's go back up here, ligase versus lyase. Sometimes people get those confused because they're similar. Remember that the ligase right here was synthesizing something with ATP to give us that ADP and release energy. Okay. Lyase is breaking or making bonds generally with this double bond. When I come down here, I do see that I have ATP, but I don't have that free phosphate over here. So I'm not going to expect this to be a ligase. And I specifically wanted to include that one because often when people say ATP, they're like, oh, done, ligase. But that's not the case. But what I do see here is that the phosphate, okay, so ATP, triphosphate, ADP, diphosphate. So this molecule had three phosphate groups, and one of those is being transferred to be bound over here. So this would actually be the transferase. All right, let's try another one. So we want to know what class of enzyme this one is. So take a minute, look at it. When I look at this, and this should be an I there, by the way. When I look at this, I'm going to say, well, I'm not transferring anything, so done. I'm not just rearranging, so done. I know that the ligase is the ATP, giving off energy, so that's not it. So I am left with this lyase, and I see I am breaking a bond, and it doesn't have to be a double bond. So we've broken this double bond to give us, or I'm sorry, we've broken this single bond to give us the two molecules. All right, that is the type of thing you should be able to do with classifying enzymes. I hope this video has been helpful.